I'm the director of the Packaging Research Center. And welcome to the distinguished lecture series. We invite an expert speaker once every 2 months as part of the seminar series. And it's our great pleasure today to welcome Professor Petru NOTINGHER from University of Montpellier in France. Professor NOTINGHER will present over a time period of around 1 hour, including question and answers. And if you have any questions, please post it in the chat box, and then we will have somebody read out the question, and the speaker can provide the answer. So with that, let me turn the floor to Professor Vanessa Smet, who would introduce the speaker.
Thank you so much. It's very special to me to introduce Petru. He was actually one of my mentors when I did my PhD, and although he wasn't my direct advisor, he gave me a lot of insight on teaching and research, and that's really shaped who I aspire to be as a faculty now. So I'm really happy to welcome him here today. So let me give a brief introduction of him. So he originally hails from Romania, and he received the first master's degrees from the Polytechnic University of Bucharest in 1995, and then a second master's degree from the Paul Sabatier University of Toulouse in France in 1996, and then he went off for his PhD degree at the University of Montpellier in 2000. So all of this was in electrical engineering. Then he transitioned into his faculty career, first as a teaching and research assistant until 2003, when he became an assistant professor at the University of Montpellier, and he became a full professor in 2012. So he's been with the Institut d'Electronique du Sud, Institute of Electronics and Systèmes at the University of Montpellier, which is a joint entity between a university and the National Research Center, CNRS. And he was the head of the Energy Systems Reliability and Radiation Research Department between 2012 and 2020. And he's then become the deputy director of the Institute of Electronics du Sud. His research is on insulating materials, electric charge measurements, and electrostatic phenomena, and he's authored and co-authored over 175 scientific publications in peer-reviewed journals and conferences, and authored also several books. And he's also the associate editor. He served as the associate editor for IEEE Transaction on industry application and IEEE Transaction on dielectrics and electrical insulation. So please welcome Petru NOTINGHER for his talk. We're very happy to have him here today.
Thank you very much, Vanessa. And first of all, so good afternoon, everybody. And first of all, I would like to thank the PRC and Georgia Tech for inviting me to give this lecture, and particularly to Vanessa. And I hope we'll have the occasion to work together in the future. So for today, what I have tried to do is a little kind of introduction in the dielectrics with some hints and some challenges. Before I start, I hope everybody can see the screen. I would like just to present very briefly my laboratory, which is the Institute of Electronics and Systems. So it is a laboratory who depends on the university and also on the CNRS. CNRS is a French authority for research. We are 240 people with 101 permanent staff, of which about 70 researchers and academia. 70 PhDs and postdoc, and 70 interns, almost. So we have about 200 publications per year and 10 patents, 20 grants, with a budget of 7 million euros, which is about $7 or $8 million, from which only 7% comes from the government. So most of our budget comes from industry. So the laboratory works on the societal challenges, which are today the industrial revival, the energy transition, the security, healthcare, the information, and the communications. We have 5 axes of research. The one which interests us today is the energy and also the reliability of system in harsh conditions, but we also work on materials, and sensors and instrumentation, and also on photonics and waves. There are 9 research teams which work on acoustics, materials, infrared lasers, terahertz radiations, and the one which I belong to is the energy and material group. So there are, let's say, 20 people involved in these thematics, with 9 permanent researchers and let's say almost 12 or 13 PhDs and postdocs. So this is where I come from. So what I would like to do now is to switch back to the lecture. So if I may just do another stop the sharing and then share something else. Okay, now okay, so everybody can see the screen. Is it okay?
Yes.
Yes. Okay. So I I gave this this lecture a title which concerns the insulating materials and dielectrics, and I say it is a key issue and the Achilles heel of present and future electronic and electrical engineering technologies. Well, this maybe this can look a little bit too daring, but in fact it is true, because we find dielectrics and insulators in a lot of places. Of course, originally everybody knows that electrical wires are insulated by dielectrics, also the high voltage cables and all the transmission cables. The overhead lines are also insulated by dielectric, which is the air. We all use capacitors, and capacitors, of course, contains dielectrics. But we also use chips, electronic chips, and well, of course, we have the tracks which are insulated by dielectric varnishes. But the most important thing in electronics today, it is the basis at today electronic, is the MOS capacitance, and the MOS capacitance is a semiconductor on which we have an insulator and the metal. It's a metal oxide semiconductor structure, and all the electronic devices today are based on this structure. So we're talking about, for instance, the modules for power electronics. When you have chips, of course, they are also insulated with an encapsulated gel. But we have, of course, this kind of elements in the power converters, which drive our trains, a lot of things in our planes, and maybe our planes entirely one day. Our cars, so the beautiful Tesla car is all electric. And of course, we have computers with electronic parts based on metal oxide semiconductor structures. And you also have this in your cell phones, in your smartphones. So we have insulator everywhere. Well, these materials are very constrained because they have to compare with a lot of requirements. They in terms of permittivity, losses, resistivity, breakdown strength, temperature, and so on. They also must withstand humidity, radiation, some fluids. They must be resistant to fire, not to be toxic. The smokes, if there are any, must not be too opaque. They must keep their properties with time. They must endure partial discharges, abrasion, flexion, markings, and above all, they must well interface with the other materials. in terms of mechanical properties. So the coefficients of thermal expansion must not be too different in order to avoid the lamination. And the electrical interfaces must match very, very good in order to avoid field enhancement and diffusion of other species like electromigrations, but not only chemical species. So we understand well when we look at all these constraints and requirements why many failures in electrical and electronic components, and in particular the most severe ones, come from the insulating layers. So this is maybe not very well known, but this is the truth. And why is this? Because of all these constraints, but because the insulating materials are very complicated structures, and it is very difficult to assess their behavior and to model their behavior too. So just to, let's say, cite some people who are specialists in properties of materials, they say electrical breakdown is a subject to which it is difficult to apply our usual scientific rigor. A well-designed insulator in the laboratory breaks down in service if the wind changes direction or if a fog descends. Well, of course, this is a little bit exaggerated, but not so much, because these materials are at the intersections of a lot of things, and a lot of assumptions that we made for other type of materials cannot be made in the case of insulators. Well, of course, as I said, there are a lot of things to say, and when I thought about this lecture, I didn't know very well how to do it. But what can I say if I cannot make an exhaustive digest of concepts and issues related to electrics and insulators, because there are many? This is not to not be a Bible to our questions and interrogations. I don't pretend to be able to respond to everything. And I can give you a generic method to set up dielectrics or to design insulating systems. So what is this lecture then? It's an insight into insulating materials, of their properties and their characterization methods, which is viewed by an electrical engineer and is aimed to electrical engineers. We will give you a bunch of hints to make you avoid some basic problems, because there are a lot of basic problems which are not, well, if they are not well treated, will lead to very heavy consequences. It's like the butterfly flaps, and I will try to give you a tool to help you to understand and to approach the challenges which are today related to insulating materials. So, how much do we know about these materials? Do we know what is a dielectric? How it works? What are its properties? How do we measure them? How it is impacted by the environment? Why does it fail? It is a very important question. And what are the challenges for the future? And do we have any leads? Well, what is a dielectric? Well, if you take a dictionary or a good physics book, they will tell you that the dielectric is a material which is able to be polarized. So what is polarization? We will come to it very quickly. Let's say that a dielectric is a material which is able to contain an electric field. So it contains an electric field. It is because it accumulated charge, and the most simple thing is a capacitor. It stores energy, so it is very well-known expression about the energy stored in the capacitors. You have 1/2 of QV. It is 1/2 of CV squared. C is the capacitance of the capacitor, which is a function of its permittivity and its dimensions. So the dielectric is defined by its permittivity. We'll look very quickly into this, and about its loss factor. But the dielectric is also an insulator. It's not the same thing. The insulator is aimed to prevent current to flow between pieces which are placed at different potentials. And you can have an example, for instance, by the insulator in a cable, which will prevent current to flow from the high voltage core to the earth. Well, in this case, you will need an important resistance, so a small conductivity. So an insulator is defined by its conductivity and also by its breakdown field, which is the maximum field it can sustain without losing its insulating properties. So just to define dielectric permittivity, you can make the following experiment. You take two plates and you apply them a voltage. So you'll have some charge, plus Q0 and minus Q0, which will come on the plates. And now if you insert between the plates a dielectric, now you will find that the charge on the plates will increase from Q0 to Q1, with Q1 greater than Q0. So if you make the ratio between the two capacitances, with the dielectric and without the dielectric, this ratio is in fact the relative dielectric permittivity, or the dielectric constant on the insulator. So the higher permittivity, the higher the charge on the plates, and the higher the energy stored by the material. So dielectric permittivity is just a way to define the capacity of a material to store charge. So of course, in the case of the flat capacitor, everybody knows that the capacitance is proportional to the surface and inversely proportional to the distance between the plates, and that the permittivity is the product between the relative permittivity and the absolute permittivity, which is the permittivity of the vacuum. Well, now the question that we might ask, how does it work? Why do we have more charge on the plates when we put a dielectric instead of the air? So in order to understand this, we must think about the phenomenon of polarization. So if you apply a field between the two plates, you will have, if you have a voltage between the two plates, you will have a field, and the field will induce the polarization, which is related to the structure of the material. So the polarization is related to the presence of dipoles, which are association of charges of the same value and opposite sign. So we can find nonpolar and polar materials. What is a nonpolar material? A nonpolar material is a material which contains atoms or molecules for which the centers of gravity of the positive and negative charges superpose. You can take, for example, an atom in the absence of an external field. If you have, let's say, an atom of hydrogen with the one proton and one electron, so with the electron which moves very, very quickly around the proton, then the center of gravity of the two charges will be the same, and there is no dipole. But if you apply now an external field, then you'll have a displacement of the charges, because the plus will have the tendency to go toward the field in the sense of the field, and the negative charge in the opposite sense. Then you will induce what we call a dipole moment. You will have an induced dipole. You will create a dipole, and the dipole moment can be defined as a product between the charge and the distance between the two charges. There are materials where the molecules have gravity centers which are already separated. So, in this case, you also have a dipole without applying an external field. And this is a permanent dipole. These materials are polar materials, and you apply an electric field, you will just orient it. So in fact, you have two types of polarization. If the material is non-polar, then if you apply a field, you will polarize it by displacing the charge from the molecules and the atom. So this is called distortion polarization. And if you have a material which exhibit this kind of distortion polarization, and all materials exhibit this kind of polarization, we will see this later, then the polarization will increase with the field, because the dipolar moment will increase, and the factor between the polar moment and the applied field is called polarizability. And if you look at the entire material, then you can define a polarization, which is in fact the number of the concentration of dipoles which are created by the external field. Well, in the case of a polar material, so all molecules have already a dipolar moment, but they are oriented randomly, and when you apply a field, they will align more or less on the line fields, on the field lines, and of course the perfect way when they all align like this one will not occur very, very quickly, not for a low field anyway, but the net some of the polar of the dipole moments will be in the direction of the field, and then you can define also polarization in the same way you define it for the non-polar materials. It means the number of dipoles which are oriented by the field. So we have distortion polarization for the non-polar molecule and the orientation polarization for the polar molecules, for the polar materials. Now, of course, it's okay, but how does it act? Why this? What happens when they are excited by the field in terms of charge on the plates? So let's take the case of the two plates when there is no dielectric, there is only air. You will have a charge Q0. Now, if you insert the dielectric inside, you will align the molecules or you will distort the molecules. So there is the ideal case when they are all aligned. And in this case, if all the molecules are arranged like this, if you look what happens in the interface between the plate and the material, you will see that a part of the charges from the plates are compensated by the charges from the dipoles. So if you want to keep the same voltage, now you have to attract charges from the source on the plates. So you'll attract a supplementary charge, which I noted here, QS. So the total charge will be Q0 plus QD or QS, which is higher than Q0. So there is more charge, and so there is a capacitance which is higher. So this is the way that explains why do you obtain a higher capacitance with the dielectric, because you polarize it, and the dipoles which are close to the plates compensate a part of the charge from the plates. So there is more charge coming from the source to compensate this loss, and we have more charge, so a higher capacitance. Well, in the case of a non-dielectric which is not polarized, for example, the vacuum, you have a field between the plates which is equal to the voltage divided by the distance between the plates. But when you polarize the material, you'll have a very strong field at the interface because there are a lot of pluses and minuses just near. So the field is not constant anymore. It will be distorted at the interface, and it will be a little lower in the bulk because the circulation of the field, the integral of the field with respect to the distance must always be the same, must be equal to the voltage. So you have three regions: the near anode, in the volume, in the bulk, and near the cathode. You can calculate easily the anode and the cathode field if you know the charge from the plates and also the permittivity of the material. And these are very, very high fields, about several hundred of kilovolts per millimeters, but the distances D1 and D1 are very small, several nanometers, so you cannot see it, particularly for thick dielectrics. So you can consider that the volume field is almost equal to V over D, because the distance between E0 and E volume, the difference is very, very small. So if you look at the dielectric displacement, you can easily understand the contribution of polarization, because you can isolate the contribution of the vacuum, which is epsilon 0 E0, from the rest, which is the polarization. And the polarization is proportional to the field, and the proportionality constant is called the dielectric susceptibility. So talking about dielectric constant or permittivity or dielectric susceptibility is almost the same thing, because the susceptibility is epsilon r minus 1. So now let's just to summarize this. The permittivity is due to the creation of induced dipoles, which might be electronic polarizations of the electronic cloud, which is distorted, or ionic polarization, the ions which are stretched, and comes also from the orientation of permanent dipoles, which is called orientation polarization. But of course, the material is never perfect, so there are also free charge. So when you apply a field, you'll also make this charge move, and these charges can accumulate at interfaces, and this will give birth to what is called the Maxwell-Wagner polarization. And this This is an equivalent polarization, which is due to the non-homogeneity of the dielectrics. So in fact, you will move all the charges which can come near the interface or which can accumulate at the points where the material is not homogeneous, and you will have charge accumulation. And this type of polarization is called space charge accumulation because it is the charge that polarizes, and this charge is in an insulating space. So this is an equivalent polarization, and if you want to look at the average polarization, it will depend on the distribution and on the charge density. And of course, it's easy to calculate it just by integrating over the thickness of the material. So there is polarization due to dipoles, and there is also polarization due to charge, which moves and accumulate at interfaces. Now, let's talk about something else, about what happens when you apply a step voltage to a material. Well, in theory, if you apply a step voltage to something, then you will just have an infinite or a very high current for a very small period of time, and then the current will drop to zero. So this will happen if the dipoles will orient instantaneously. But this is not the case. The dipoles need some time to orient. So you will never have an instantaneous polarization of the material. It will have some time. So if you look at the current that you're measuring, it will reach zero after a time t1 and not after an infinitely small time. This holds only for vacuum. So you have a component which is due to vacuum and the other one to the polarization. Well, now the material is not perfectly insulating, so you'll also have conduction. So there will be free charge which will be displaced, and the polarization current will not come down to zero, but to a value which is equal to the value of the conduction current. So you have the conduction component which is here. And in reality, you'll also have some movement of charge inside the material, and this will give you a current which is not perfect like this, but you may see some zones where the current rises and then falls down, some oscillations, and these are space charge oscillations, the charge movements inside the insulator. And if your insulator is a very good one, you will wait a very long time until the current drops to the conduction value. So this current is called the absorption current, and you will see all the components here. It is the polarization component that will come to zero when all the dipoles are oriented or distorted. It is the conduction component and also the component which is due to the movement of charge, which will not travel across the entire distance between the two electrodes, the space charge component. And all these things need energy. You need energy to orient the permanent dipoles, which what we call dielectric hysteresis. You need energy to stretch the atoms and the molecules to make induced dipoles. This is also dielectric hysteresis. And you also need energy to displace charge carriers across the dielectric. So in order to move them, you will need energy, and this will lead to heating, and this is what we call dielectric loss. So to account for the electric loss, you can use the complex permittivity of a material. And in the complex permittivity to the real component, it is the one we were talking about from the beginning, you can add a component which is in fact the image of the lossy character of the material, which is in fact which includes the conductivity and also the loss of energy due to the dipolar orientation. So this will be in fact the equivalent of considering a material like a capacitor with a resistance in parallel. So this will mean that a non-ideal dielectric or a real dielectric will be in fact not completely reactive, but it will be also a little bit resistive. And you will have an angle between the current absorbed by the dielectric and the voltage applied, which is not equal to 90 degrees, but a little bit smaller. And this angle, the difference between 90 and the angle between the current and the voltage, is called the loss angle. It is in fact the angle that defines the power, the active power that is consumed by the material for orienting the dipoles and for the conduction. And we can define the tangent of this angle, which is the tangent delta, which is in fact the ratio between the active power consumed by the dielectric and the reactive power it furnishes. Well, now, if you move the frequency, we will have different responses, because the different entities, the different dipoles that you have in a material will move more or less with respect to the frequency. So when you have a low frequency, you will be able to move all the dipoles, to make oscillate all the dipoles in the material. But when the frequency increases, the biggest ones will not be able to move anymore, and after a certain value of the frequency, we will not they will stop to move, they will not be able to oscillate with the field, and of course the permittivity will drop. And in the same time, you will see what is called the loss peak. In fact, an increase of an important decrease of the tangent delta, or the imaginary part of the permittivity. And this will happen for the dipoles, and then it will happen with the atoms or the ions for higher frequencies because they are smaller, and also for electrons at even higher frequencies because they are even smaller. And the dielectric spectrum of a material will have one or more such relaxation peaks. So the relaxation peaks correspond to the frequencies for what a kind of dipoles is not able to oscillate anymore, and then the permittivity drops. So of course this is an interesting thing to do, because the frequency, of course, where this relaxation takes place will result in a high loss. So you don't really want to use your material at a frequency like that. So it is an interesting thing to trace the dielectric spectrum of the material, and this, in fact, is the measurement of the voltage and the current when you apply a voltage of given frequency with an apparatus which is called a dielectric spectroscope. So you can calculate the impedance, the AC impedance, the imaginary impedance of the sample, and then you can draw from this the real part of the conductivity and the imaginary part of the conductivity, and or the permittivity. I'll talk about the conductivity later, and also the loss factor. So it's a very easy modeling. Of course, you will not use samples like this because you don't want the parasitic capacitances coming from the edges to be taken into account. So you will use a guard ring. Well, you will use a source of variable frequency if you want to have all the spectrum, and you will use a low current instrument to measure the current, the module, and the phases. So this is your dielectric spectroscope, and you will have all the dielectric spectrum of your material. And these are some examples. You see, for instance, on epoxy which is filled with alumina, this is a spectrum which starts at 0.1 hertz and ends at 1 megahertz. So we're not going to the frequencies where you're seeing atomic or electronic polarization. This is the normal use for a material in electrical engineering. And you can see that here you have three peaks, a peak which is here, another one which is here, and you see that it increases, that you can imagine that there is another peak, but which is out of the spectrum. And when we increase the temperature, as the molecular mobility increases, the peaks will shift to higher frequencies. So you see this peak which shifts above 100 kilohertz, and when you increase a little more the temperature, you won't see it anymore. This one will be here. This one will come closer to the kilohertz, closer and closer. This, we still have the secondary peak. You see more and more this one, And when you go to 125 degrees, you have the main peak, the one that you're not able to see here because it is below 0.1 hertz. And you don't see the relaxation, secondary peak anymore. So in fact, this allows you to see the dipolar movements. So this allows you to analyze the material behavior. This allows you to see for a given temperature, what will be the losses that corresponds to your material in order to be able to calculate the heating of your object for which you use this material. So you will be able to set correctly up an insulating system for the given application. Well, as I said before, you can also draw information about conductivity. So this is the relaxation peak. So this is dipolar. But if you go enough low in the frequency, you can encounter a slope of -1 in the epsilon second on your spectrum, and as the imaginary part of the permittivity, it is in fact the same thing as the conductivity. You can draw from this directly the conductivity of the material, what you call the pure ohmic conductivity. It means the conductivity which is due to charges, which goes from one plate to the other. It travels completely across the material. And it is very easy to do that because you have this expression, and you take one value from here, you use the expression, and you calculate the conductivity of the material. So this is the real conductivity, the one that is defined in the sense of a metal. I mean, the charge which completely crosses the material. Sometimes you don't see a slope equal to -1, but higher than this one. Why? Because there are charges which are stopped at the interfaces, which I call the Maxwell-Wagner polarization or the electropolarization. And this, you will be able to see it. And unfortunately, you won't be able to draw the conductivity from this. You have to have a slope equal to -1. And this slope, you don't have it always. So you must take care of this. Well, of course, it is very easy to draw a conductivity plot because the relationship between conductivity and permittivity is just the permittivity multiplied by omega and epsilon 0. So you can draw a real part of the conductivity and an imaginary part. And if you plot the real part, you see very well when you reach a plateau, the conductivity is constant. So this is the value of the conductivity that you want to measure. So this is an example done on mineral oil. So you see very well the conductivity of the oil with respect to several temperatures. So of course it increases with the temperature, which is perfectly normal. So this works very well if you have a high level, low frequency spectroscope, which is very expensive. And if the conductivity of the material is not too low, because if the conductivity is too low, the current that you will measure will be very low, and your spectroscope will not be able to measure it correctly. So if it's not the case, what can you do? Well, if it's not the case, you can do what the definition of the conductivity says. So you take a high voltage source, you apply the voltage, you measure the voltage. So you calculate the field across the sample, you measure the current, you calculate the current density, and then you apply the Ohm's law, G equals sigma E, and you get sigma or the resistivity rho. Of course, you will use guarded electrodes to avoid the surface currents to be taken into account for the measurement of the conductivity. So the surface current will go to the ground and will not be measured by the current instrument. Well, is it so easy in practice? Well, not necessarily, because the time until the steady current, which is needed to get the conductivity, will take, it can be very long. So how long? Really long. For instance, here, there is a measurement done on 1 millimeter epoxy resin by applying 1 kilovolt. So the field is 1 kilovolt per millimeter. And you see that after 600 seconds, so it's 10 minutes, the current is still decreasing. So we're still here. We have not reached this area. And for very good insulator, you can wait hours, dozens of hours, days, weeks, especially if the field is low and the temperature is low, because then the current will be low. So you will have to take quasi-steady state measurement time. So I mean, you know that you have not reached the steady state, and you must accept this as here. So you use periods of time where the current is almost constant, but not really constant. A way of looking at this is, of course, to plot the current during the time in a logarithmic plot. And you will also want to take some more measurements, not only 1 point, by increasing the voltage. And you'll also have to discharge the sample between 2 measurements in order to suppress the memory of the material. So, why you should do? I was talking about the memory of the material. Why you should do that? Because in fact, if you increase the field, you may have, and you will certainly have, the surprise to see that the material does not behave linearly above a certain field. So this is an example of a sample on which we have measured discharge currents. You see that here the current has almost the same shape for the low voltages, for the low field, and is almost proportional to the voltage. And then after 3 kilovolts, then the shape of the current changes, and a lot, and this has nothing to do anymore with the absorption current that we shown before. And why this happens? Because you will inject a lot of charge at electrodes, and the injection will increase with the field. So you do not fulfill anymore the ohmic conditions. You have, of course, the polarization current, which always stands and you only increase, but you also have a current which is due to the injection of the charge. And this current will cross the polarization current, will become predominant, and this is why you may encounter this type of measurement. So this means the significant charge injection may occur at electrodes under high field and temperature. And this is due, also this may be done because when you polarize the material, the field between the dipoles and the electrode will increase as more and more dipoles will be oriented, and this will favor injection. So you have the two phenomena that act together, and the result will be a very high electronic current, and your insulator will not behave at all as you expected as a low field. So this is why insulators are known to present a nonlinear behavior. So that means you have a slope, a constant slope when you trace the current versus the voltage for the low voltages, and this is what we call the ohmic region. And after some value of the voltage, you will have a non-ohmic, non-linear dependence. So you can trace the same plot if you want to get rid of the geometric dimensions of the sample in current density with respect to the field. So in this case, you have the slope in the low field region, which is equal to the conductivity, and afterwards you will see that the conductivity will start to depend on the field. So this is called the current voltage characteristics, and it is a very important criteria to assess dielectrics. So as I said, you have, if you plot G versus E, you have these characteristics, and if the slope here is a constant, then when you plot it in log-log, you have a region when the slope is equal to 1, and this is what is called the ohmic conduction, the classical conduction. And after some value of the field, then you will have slopes which are higher than 1, and which will account for injection on, or what we call non-ohmic conduction. That means localized conduction, not from one electrode to the other. Well, in reality, it's not so nice. You will get measurement points which will be scattered, but you will be able eventually to align them on this kind of slopes. Well, these are some examples that are shown here, and of course you see the slope equal to 1 in this case. Here you see a slope equal to 1, and here you see no slope equal to 1. Maybe the field is not low enough to see the low field region. So just to summarize, If the fields exceed several kilovolt per millimeter, the current voltage behavior of the insulating material will be highly nonlinear, and you can identify a threshold region between the ohmic and non-ohmic region, but not always. The temperature is also a very important factor, because this behavior is highly nonlinear. As you can see here, the conductivity will increase a lot, even if the temperature increases only of 20 or 30 degrees. So it is important to understand that you cannot use a classicum on low, and you must not use it to approach the electric in service at high stress. So if you take the resistivity of your material from a manufacturer, you must know that this resistivity is only an indicative value and will not stand for high fields and for temperature above 40 or 50 degrees. Okay, so maybe if there are questions, maybe we can take some questions. Okay, so if there are no questions, we can proceed. So how do you do for the high field region? If you want to use your material in a high field region, you have to analyze your material with respect to the conduction mechanisms that take place at high fields, and there are many. There are a few. Some of them are interface mechanisms. Some of them are bulk mechanisms. But why would you do this? Because it can be well, sometimes difficult. You need to understand the phenomena that take place in materials and structures, and if you want to set up an insulating system, you want to have an expression to be used for field and heating calculation. So this will give you the possibility to determine if your material is suitable for a given application. Will it stand what you want? How do you use it, and how do you design your component? So the charge transport in insulating materials obeys to some laws. The most known one is the Schottky law, which will govern the passage over the energy barrier at the interface between a metal and an insulator. It is a very nonlinear and highly temperature and field dependent law. If the fields are very high, above 100 kilovolt per millimeter, then you'll have tunneling. Tunneling is a quantic effect. This means that the charge will not jump over the barrier, but it will travel across the barrier. And in the bulk, you will have also what is called hopping. So that means that the charge will move from trap to trap in order to ensure conduction. So this phenomena of trapping and detrapping of the charge is the most important in dielectrics, because there are not many free carriers. There are very few. So the conduction in the insulating materials occurs mainly by hopping, and the injection is due by Schottky effect or follow-node effect for very thin layers, because you have to have very high fields. So this will give you the characteristics which have slopes that are superior to 1, V2, V3 over D2, etc. So this dependency of the characteristics, this characteristic will depend on the trap distribution and on the distribution of the energy of the traps. The most famous one is the space charge limited current, but it is not the only one. So just to summarize this, the conduction properties in an insulator, they are controlled by localized states in the band gap. These are by defects, and these traps, they assist charge transport, charge injection, and they may be responsible for charge accumulation, which is called the space charge formation. And in fact, they are due to defects, to chemical defects or to physical defects in the insulator. And you cannot make a perfect insulator. You'll always have some. So at high fields, the charges are injected into the material at interfaces. They are trapped and detrapped. And of course, with respect to this dynamics of this phenomenon of trapping and detrapping, you will have the current through the material. You will not have a constant current, and you'll also have a field distribution, which is not which will be very different, which may be very different from the constant field V over D. So what are the effects of this space charge? If you inject charge and if the charge is trapped and it stays in the traps, then you'll have an enhancement of the field, and this can be very spectacular. For instance, if you have hetero charge, that means charge that it has a sign opposite of the electrode. Like here, you increase the charge at electrodes, that you increase a lot the field of the electrode. So instead of having 20 kilovolt per millimeter, you will go to 40. It's exactly the same thing that you have when you polarize the material. But if you inject the charge over an important thickness, so this field will be high on an important thickness. So this can be very detrimental to the material, because instead of having 20 kilovolt per millimeters, you have 35 or 40. Well, if you accumulate charges which are of the same sign on the electrodes, we call homocharge, then you have, of course, a decrease of the field near the electrodes and an increase of the field in the bulk. So this is maybe less dangerous because it will not increase so much. It will increase of 5 kilovolt per millimeter, 5 kilovolt per millimeters here. But anyway, your insulator will be over solicited in the bulk. So this is also detrimental to the insulator. So I would say that you should measure the charges. Why? Because of course more charges, more electric field, and if the field, the sum of the applied field and the space charge fields is above the material threshold, then the system will fail, and this will give, of course, birth to all the security or economical issues we were talking at the beginning of the lecture. Just to give you some order of magnitude, and this is very interesting because you can see what is the idea. If you consider a field, a space charge field at 300 kilovolt per millimeters, which is the breakdown field in polyethylene, this will be the equivalent for a 1 millimeter thick uniform distribution of charge in polyethylene of only 1 electron per 1 billion molecules of ethylene. So you have 1 electron for 1 billion molecules. It is clearly much smaller than the accuracy of any fabrication process. So this means that you will have charge from the manufacturing, and it will increase, and you will not be able to, if you don't measure it, you will not be able to detect that you will have some regions with such a high field in your material. Just to take another example, if you design your insulator for an applied field, let's say of 30 kilovolt per millimeter, and you want to last it for 40 years, of course, you will assume that your field is constant. But if you have space charge, let's say if you have space charge which will give you a field of 5 kilovolt per millimeter, that means that you will have a field in some region not of 30 kilovolt per millimeter, but of 35 kilovolt per millimeter. So it doesn't look a lot, but if you look at what happens with time, so if you have a time to breakdown low, I took this one because it's one which is used for high voltage cables. This will, by increasing the field from 30 to 35 kilovolt per millimeter, instead of 40 years of service, you'll have only 8 years and a half. So we will reduce your lifetime by a factor of 5. So this is tremendous. You have several percent, and you have a field in plus, and you will have a significant reduce of the lifetime. Well, of course, the effect may be lower, but if you reduce it by 2, it's not. It's very complicated too. So you have to control it and you have to measure it. So how do you measure it? There are several methods. The idea is to perturb the electrostatic equilibrium of the sample, and then to get a response which is a function of the charge and field distribution. There are several ways to perturb this equilibrium: thermal waves or acoustic waves. So this can be thermal perturbation that will give you an electrical response. And there are some methods which are in function of the perturbation you use: thermal step method, thermal pulse, etc. You have acoustic method when you use a pressure pulse, and you will give an electrical response. And you can also use an electrical perturbation or voltage pulse. You will have Coulombian force between the perturbation and the charge. This will produce an acoustic wave, and you can measure this acoustic wave, get an electrical signal, and get the charge from this signal. This is called the PEA, pulse electroacoustic method, which is a very used method over the world. So these methods are very interesting because they are non-destructive. They are applicable to a wide range of dielectrics and geometries. And just to give you an image of how it works, I will choose a thermal method, which is one we have invented in Montpellier. It is a thermal step method. So what's the idea? If you have a charge in the sample, then you have influent charges as electrodes, because you have a system where the total charge must be nil. So Q1 plus Qi plus Q2 equal to 0. So if you look at the current in the external circuit, if the sample is at equilibrium, you will measure nothing, because what you would measure is the variation of this charge, and when this charge is constant, you will measure nothing. Now, if you apply a thermal wave, the material will start to displace. You will have displacement of the charge, and this will give you redistribution of the electrodes, of the charges of the electrodes. This will mean a variation of the charge Q2, and this will give birth to a transient current, which you will measure. This current is a function of the field over the thickness and of the temperature, and by solving this equation, you can get the charge distribution and the electric field distribution. So the real field is the insulation. So you can get nice signals like this. This is a virgin sample, so the current is not nil, because, as I said, there is also some charge even in a virgin sample, and then it depends on the constraint. And from these currents, you can draw the charge profiles. So you can apply the same principle, which is here for the flat structure, to a cable, and then you'll have the field with respect to the radius. And you can, of course, build industrial installation which will help you to qualify the cables and the material for the cables for an industrial use. So here are an example of currents that are measured and then field distribution that are measured on cables in an industrial facility. And here are some examples of what you suppose the distribution to be in a cable. So either a capacitive one or a resistive one, but in fact you have nor one nor the other. You will have fields that can be much higher than the one that you expect. Well, as I said, there are some other methods. I will not go into details because the time is running up. Well, there is no best method. All methods are complementary, and you will use it. You use one with respect to the application, to the sample, to the thickness, to the technical requirements, and so on. The most used one are the thermal step method and the PA. Okay, so I'm approaching the end, and the last thing I wanted to talk to you about is breakdown. So what is the breakdown? It's what we don't want from an insulating material. It is the loss of the insulating properties of a material, which is permanent for a solid, and is temporary for a gas or for a liquid, because when there is no hole in the fluid will auto-cicatrize automatically. But in a solid, it is permanent, and you can define a breakdown voltage and a breakdown strength, which is in fact the maximum field that can be applied to the material without the loss of its insulating properties. Well, of course, breakdown it has been analyzed, and there are some theories with respect to the breakdown. The first one is the electromechanical breakdown, when you can suppose that the compression of the insulator by the electrostatic force, F equal Q E, will compress the material, and if this effort overcomes the mechanical resistance, then the insulator will break down. So the model is very, very easy to do. If you make the calculation, you will find that the breakdown voltage is depend on the thickness and also on the Young modulus and on the permittivity. And of course, if you divide everything by LBD, you will find that the breakdown field is not a function of thickness. So it's a function of the Young modulus and is inversely proportional to square of epsilon r. So we can observe, we have observed such behavior in thin layers of silicon dioxide. You see that whatever the thickness here, the breakdown strength and the lifetime is the same. So this is an indication of an electromechanical breakdown. The problem is that the values which are predicted by the theory are higher than the observed one, maybe because the real field of the field in the dielectric, real value, is not V over D. Another theory which works well on thick materials is the thermal breakdown theory. When we consider that the heating of the material, which is due to the Joule effect, would be so important that the material will endure a thermal runaway, and then it will break down. And then if you write the thermal balance of the material, you can draw an expression of the breakdown fields, and you see that the breakdown fields is proportional to 1 over square of the thickness. And this works quite well in medium and strong thickness materials, as the example that I have here. You see that if you plot the breakdown strength over the thickness power 1 over 2, you will have a straight line. So this is the witness of a thermal breakdown. You can even calculate the time to breakdown if you neglect the exchanges by convection by considering that there is a thermal runaway. But in practice, these lifetimes are not the same that you predict by theory, and the real breakdown is not a breakdown over the entire material, but only over a filament. So this is not it will not give you the good values, but the law of the breakdown strength between with respect to the thickness would be respected. And in fact, the last one is the avalanche breakdown theory, which in fact is the same as in a gas. So we assume that an electron which is accelerated will ionize a molecule, and then the molecule will release another electron which will ionize another molecule, and so on. So at the end, we will have an avalanche, which will be in fact composed of a lot of electrons, very, very energetic. So this is a current which is very high. This will destroy the material. Well, of course, this will work if the ionization energy of the atoms is high enough, and there are a lot of hot electrons. And if this is the case, you will have a breakdown field, which will have this expression. You have the log on L0, which L the thickness of the material, and L0 is the acceleration distance of the electrons. So this relationship is quite well verified in thin films without defects, but not in necessarily for other thickness. And of course, because it is supposed that the electrons are not trapped, and this is purely impossible if the material is too thick. And also, if it is too thin, the electron will cross the material without ionizing anything. And it does not account for the decrease of the breakdown field with time. So, all these models do not account for reality, except at very short times. But what do we know about breakdown? If the breakdown, it corresponds to current instability above a given field, which will give birth to a local destruction of insulation. And this destruction is due to a thermal runaway, which will occur because some material property will change with temperature. The typical breakdown fields are above 10 power 8 volt per meters, and even 10 power 9 for very thin layers. But these values can be significantly lowered if there are protrusion, voids, and space charge, as we've seen before. So, if you want to measure the breakdown field, the breakdown strength of a material, you can just do this. So, increase the voltage by steps until your material breaks down, and then you can have a value, and you will see that this value will depend, in fact, on the measurement protocol. So on the width of the steps, on the height of the steps, of the ramp speed, because you can also use a ramp to break your material. It will depend on the thickness of the sample. We have already seen that. It will depend on the temperature. So you have some examples here. You see that there are drops in the breakdown strength with temperature in a lot of materials. It will depend on frequency, which will also depend on the duration and the condition of the application of the stress. So it depends on the aging of your material. So the breakdown will decrease with time. So it is not easy to predict what will happen with the material. So there is a small diagram here about the theories that I presented you before, which will give a time to breakdown, a very small time to breakdown. But for the long times, other mechanisms which will degrade the material will take place. And we're talking about treeing, about electrical trees, water trees, or partial discharges. A total destruction of the material is almost never observed. If you look at this picture, you see that the crater of the breakdown of a silicon layer, it's only 3 microns. So there is a small hole. It's not the entire surface of the film. Here there is another example with the thick insulator where electrical trees have developed. The length of the trees will increase with the voltage. So breakdown is a local phenomenon, and this is a very important thing to understand. So the most important role in breakdown is the role of local defects, which will lead to the formation of conducting channels, which will then be the subject of thermal runaway and will give to breakdown. And as the number of defects in the material increases with time, the breakdown strength diminishes also with time. So this is the phenomenon of aging. But the aging is a global phenomenon. It's not a local one. So the material will age globally, but it will result in some weak points in a local breakdown. So as the theories are not taking into account the role played by these defects, they are difficult to be used for estimating the evolution of the breakdown strength with time. And this is why there are significant security factors that are taken in the design of the insulating systems. And also because of this local characteristics of the breakdown, you will have very scattered data and you will need to make many tests and you will need to treat them statistically. Well, just to summarize what we know and we don't know about breakdown, I will just say that the breakdown will start and will take place very, very quickly. It will have a catastrophic effect. And the aging and the degradation are much longer phenomenon, and they are not very easy to observe. So this is why life modeling needs to take into account the localized nature of the breakdown, the synergy of constraints, temperature and field, and also scaling laws, because when you're making experiments, you're making them on thin samples, not on samples that are 1 millimeter, 2 millimeter, 3 millimeter thick. So it is very difficult to expand these values to the real size of the insulating systems. This is why there are many models today, and this could be the subject of an entire lecture. But there is still a lot to do in this area for people who are interested in. So we know a lot of things on dielectrics, but as you can see, there are a lot of things that we don't know, and we don't really know how to model them. To model conduction, space charge, and aging is very difficult because these are local phenomena. So how to integrate them? This is a big challenge. We don't know very well how to integrate scale effects, as I said before. And we know some things, but not enough about the interfaces. What happens in interfaces? Interfaces are the weak points of every insulating systems. And what we'd like to do, and we know more and more how to do it, is to tailor material with specific properties, I mean gradients of conductivity, of permittivity, by integrating nanoparticles and so on. So what are the new challenges? And this will be the end of the talk. Just to give you some insight. Well, they are related to the challenges that we have today in energy transition, which are the electrical power transport on long distance. We all want wind farms, but we have to connect them to the ground. We have to interconnect the networks to ensure the security of the supply. We all want to do electrical mobility. Even the all electrical aircraft is not a dream anymore. We are talking very seriously about hybrid electrical planes and about more and more efficient electronic devices. So, if you're talking about electrical power transport, you have to bring the energy from offshore onshore, and you also have to interconnect the networks. And this must be done by submarine cables. And this is the plot of projects, which are projects of common interest in Europe. And you know there are many. And the only solution to this are high voltage DC cable links. And the question is why? Because if you take an AC cable is a capacitor. So you have a capacitor, you will have a capacitance current, omega CV. So this capacitive current will also be absorbed by the cable, even if you don't supply anything. So if you don't have a charge here, you will also have the omega CV. So this no load capacitive current will affect the useful current, because you have to subtract it from the maximum current that you can deliver. And for a length, a critical length, you will have no more power which can be transmitted to the load. So, for instance, here for this case, after 50 kilometers, you will not be able to supply anything to your consumer. Now, if you use a high voltage DC cable, omega equal to 0, so there is no more capacitive current. So there is no length limit for an HVDC link. You have losses that are lower than in AC because there is no electromagnetic field. So there is no eddy currents in all the neighboring parts. You will be able to have higher fields in the insulation. So this is what we expect, 50% more. So it means better efficiency. You may have control of the active and reactive power. So these are the converters. And you also can connect non-synchronous networks, and you will have less costs if the distances exceed several dozens of kilometers. So why these systems are not so widespread? Because there is a bottleneck, and the bottleneck is the cable. So oil and mass impregnated paper cables have been used, but there are problems relating to maintenance, and the synthetic extruded insulation need to fulfill all these requirements. And the problem is that the service construct, which are a high DC field, a field gradient, and a temperature gradient, and the reliability constraints make that we do not have enough appropriate insulating material and structures. So we need materials to fulfill these constraints. And why does it happen? In an AC cable, you have a capacitive distribution because you have there is no resistance in AC. Now the resistance of the insulator it doesn't count. It's only the capacitance. So the electric field is controlled by the permittivity, but in DC you will have the resistance and you won't have the capacitance. So the potential will be controlled by the resistivity, and the resistivity as you saw before, varies a lot with the field and the temperature. And moreover, you will also have space charge, and this will distort the field even more. And this means that you will have to deal with this. And the main bottlenecks for the spreading of HVDC transmission is the insulating materials for cables and accessories. So there are a lot of things that must be fulfilled by this insulation. I will not go too deep into this, but there are many. And all of these problems are not yet solved. So we have a problem which is quite similar in the in the electrical mobilities and for the airplanes, the more electrical, even the all electrical airplanes, for the automotive and for the space propulsion. So we have increased a lot the power in the airplanes. We are now at more than 1 megawatt for the B7 and 87. And if we want a hybrid airplane, we will go up to 10 megawatt and even to 20 megawatts. And this means that the onboard networks will have to be above 800 volt or even 3 kilovolt, and today we are only at 270. So there is a huge increase in these values, and this will translate in the increase of the temperature. Because if you want to do this, you must use power electronics with SiC SiC dies, and you will need insulators which will be able to sustain all this, to withstand all this temperature and also the increasing field, because you want to make them more compact. And the same thing with the cables. There are several hundreds of kilometers in an airplane. You have to make them withstand the HVDC, the new form of stress which are given by power electronics, and also the electrical machines, which are the generators, for instance, for hybrid airplanes, must withstand much higher constraint, and you need high breakdown strength insulating materials. So I listed here some challenges, but I will pass on this. And the last one is about electronic devices. In every electronic device, you have a MOS capacitance. So you have a gate insulator and a passivation insulator. And if you want to integrate more, to reduce dimension, if you want to go to the nanometer, then you will have to build new gate and passivation insulators to replace the SCO2, which is now almost to the limits. So this is an interdisciplinary field. It's the interface between physics, chemistry, and electrical engineering. And we need electrical engineers. Highly applied, there are many challenges, and there are also many opportunities. And I hope this has interested you, and I apologize for the time.